So we're going to be looking at 12C absolute maximums and minimums. Absolute maximums and minimums occur when between an interval, let's say A to E in this diagram, it is the X value that gives the highest Y value in that interval. And an absolute max or minimum can sometimes be referred to as a global. So we use absolute or global to represent those maximums or minimums that are there is nothing that is greater or less than those points. So there's no Y value within your interval that goes above those points. We then have what is sometimes referred to as relative or local maximums or minimums. And these are where we still have a turning point within the function, but it is not a global or max. So there is another point within the interval that is still higher than that one. So all turning points will lead to maximums or minimums. So for example, we have a local maximum here. We have an absolute maximum up at the top here. And down at the bottom, we have here a local or relative minimum. It is important to note, though, that not all stationary points are turning points, and consequently not all stationary points are maximums or minimums. So if you set your first derivative equal to 0 and solve, we would have also found this point here and this point over here. Now both of these 2 points, so when we did our first derivative and set it equal to 0, we would have found 1, 2, 3, 4, and 5 values from doing that. And at that point, only 1, 3, and 5 are actually maximums or minimums. Points 2 and 4 are stationary points, but they are points of inflection. So we have to be careful that we don't just assume, or when we set our first derivative equal to 0, that all points that come out from that will necessarily be a maximum or minimum. And the way we can check that is by either using a sign diagram. So we can have a look here. If we had something that where, let's say this is point 2, we would have seen that before this we would have had a negative gradient, then a horizontal gradient, then a negative gradient. That is showing that around that point 2 it is a point of inflection. Another way we could have shown that point 2 was a point of inflection is actually subbed in the X value for point 2. So if I had subbed in X of 2 into my second derivative, if I can get my pen to work, if it's a point of inflection, this would come out as 0. So we can use also a second derivative function to help us figure out whether things are maximums or minimums or points of inflection. And important to note, it depends on the question which method is more efficient. If it's easy to differentiate twice, then using and subbing in values is not too onerous, then yeah, using your second derivative is a great way to check whether things are maximum, minimums, or points of inflection. If, however, finding that second derivative is going to take a long time and be a bit of a laborious process, then definitely using your sign diagrams would be the quicker method to do that. So just be aware that there is a few different ways of doing it. Now, the other thing to make a note of from this diagram is that these points down here, this one here is our absolute minimum. It is the lowest value Y takes within the interval A to E. However, we can only endpoints within a domain when they're not turning points. They can only ever be absolute maximums or minimums. They cannot be local. Local has to be a turning point within the function. So this guy over here is not a local minimum. He is just nothing. He has no name to him. So this diagram only names the positions that, the points that are the absolute or relatives. So point 5 is it is a relative maximum. It's a local maximum within that area. But obviously the fact it's an absolute maximum sort of overweighs that bit. So 5 is an absolute maximum. C is a relative minimum or a local minimum. Number 1 up here, or B in this case, is our relative maximum, so it's a local max. and A is our absolute minimum. So an endpoint of a domain can definitely be an absolute max or min, but it cannot be a local. All right, our first example then, we have x squared plus 3 over the interval -2 to 3. So definitely with a function like this that you should be able to sketch, it would be best to sketch this function to help you figure out what is happening here. So we obviously, if I did a very quick sketch just to begin with, this is the x squared function moved up 3 units. So we've got a U-shaped positive U that looks something like this. Now, we need to be aware that we actually have a domain on this. So it means that we are only looking at values that go from -2 to +3. So what that means is we're actually only interested in values from here to here. So our function, if we are actually to draw that properly, is going to be, here is my 3, so we're going to, and here is my -2. It has closed circles on the ends because they're square brackets. We're going to go through our function, and then over here will be 3, so a bit further along. And the function is going to look something like this. To figure out these coordinates, so it's really important that we find the y values at all these points, because that is the value that takes the maximum or minimum. So our y value at the intercept will be 3. To find the y value for this point here, the first point, we need to sub -2 into the function. So we're going to say then f of -2 is going to be equal to -2 squared plus 3. So it's going to make 7. So the coordinate point here is -2, 7. And the coordinate point of the second one, so it's this one up here, this one is going to be f of 3. So we'll get 3 squared plus 3, which makes 12. So this one's going to be 3, 12. Now we need to decide what is an absolute maximum minimum and what potentially is a local maximum or minimum. So looking at these points, we can see this point 312 is actually the highest point that the highest y value that the function takes within this restricted domain. So what we can see is this one here is actually an absolute maximum. And what we can also see is that our absolute minimum occurs at the cross of the y-axis. So this here is our absolute minimum because it doesn't go anything below that point. Now the final value, the final point that we need to be careful about is this end point on the other side over here. Now this guy here, he is neither an absolute or a local. He's not an absolute because there is a lower point than him, and also he is not a local because ends of domains cannot take local maximums or minimums. So what we now need to do is just write a quick summary of our findings. So we need to then say the absolute maximum occurs at x equals 3, and f of x at that point is 12. And our absolute minimum, trying to get my pen working, so my absolute minimum occurs at x equals 0 and f of x will equal 3, and that's our turning point through the middle. That's 3. That's 0, 3. Okay, so moving on to the next example then. Our next example says find and state the nature of all absolute and local or relative maximums and minimums of this function. So in order to do this, we can't just necessarily sketch that straight out. So what we're going to do then is use a combination of solving for y values and using our first and second derivatives, or maybe sign diagrams, to solve this problem. So we know that when I have a restricted domain, we need to really think about this domain and what impact that would have. And we need to think about what y values occur at that point. So whenever you get a domain, always make sure you sub that into your function to find the coordinates of the y value. So we're going to have a look at what f of negative a half is first. So I get negative 1/2 cubed minus 3 lots of negative 1/2 squared plus 3. So I get negative 1/8 minus 3/4 plus 3. And if I put that all into eighths, I'm going to end up then with an answer of 17/8, which I guess is also the same thing as writing 2 whole ones and 1/8, just so you get an idea of what that number is. And so we have the coordinate point then of negative 1/2 and 17/8. I'm going to highlight that guy in yellow because we need to bear him in mind when we think about maximums and minimums. We now need to also see what the other side of our endpoint is, so 4 needs to be subbed in. So we need to find f of 4, and f of 4 is going to be 4 cubed minus 3 lots of 4 all squared plus 3. So I'm going to go 64 minus 48 plus 3, which gives me 19. So I have the coordinate point 4, 19. So let's just highlight him as well. Alright, now we need to have a think about turning points. So turning points, remember, not always a maximum or minimum. I should say always. So we need to be aware of that. Our first derivative is equal to 3x squared take 6x. And so we can solve then, if we set this equal to 0, we find our turning points. And factorising it and solving it, I'm going to get x is equal to 0 or x is equal to 2. Now we need to check whether these are turning points or whether they are points of inflection. So we need to check using either a sign diagram, or in this case it will be quick and easy to use our second derivative. So our second derivative is 6x takes 6. So subbing in our value of x equals 0 into this function, we get f double dash of 0 is equal to negative 6, which is less than 0, therefore it is a maximum point. So we know it's not a point of inflection because we don't get a second derivative of 0, we're getting a second derivative of negative 6. And our next one we need to check is when x equals 2, so we find the second derivative of 2, which is actually going to just equal positive 6, which is then greater than 0, therefore that point will be some form of minimum, either absolute or local. Now, what we want to do is actually find what are the y coordinates for those points so that we can compare them all. So if I now sub in x is 0 into my function, I get f of 0 is going to be equal to 0 cubed minus 3 times 0 squared plus 3, which gives me an answer of 3. So we have the coordinate point 0, 3. So that's another point. And we also have f of 2, which is going to be 2 cubed minus 3 lots of 2 squared plus 3. And that will give me an answer of negative 1. So I get 2 common negative 1. So then we get that point of 2, negative 1. We can actually sketch all this together. So we have the point of 4/19 and negative 1/2, 17/8, which was from the endpoints of the domain. We then have our two turning points of 0, 3 and 2, negative 1. Looking at the diagram, we can see we have an absolute maximum of an endpoint, which is absolutely fine, and that is of 4 and 19. We have a local max at 0, 3 and an absolute minimum of 2, negative 1. Remember that the other endpoint though, because it isn't an absolute, we leave it off. It has no maximum or minimum associated to it.